Okay, so thank you everybody for being here. And we also wanted to thank Berkeley and this conference for inviting us to share our capstone. So we were students until very recently, so we very much understand what it's like to sit in this room. And we're excited to share our capstone project with you about baseball. Hopefully, even if you're not a baseball fan, there'll be something for you to take away from our presentation today. So I just wanted to orient you. This is one of the later presentations, and you've seen a lot. So let's just give you some context. This is our agenda. First, we're going to start, and there's three of us, so we're going to go kind of in turn here and then come back together at the end. First, we're going to talk about the problem that we tried to solve and explain a little bit about some baseball rules. Next, we're going to talk about the solution, what our system actually did. We're going to go into detail about how it works, and Josh is going to come up and explain those portions. Then we're going to go into the results, and the how it works and results is where Zach comes in. We'll all come back, and this is special for this presentation because we know we're speaking to other MIDS students. We will talk about some lessons learned and something that we can abstract away from our capstone project that will be hopefully useful to you when you do yours, and data science beyond the scope of this course. And then at the end, we're going to leave plenty of time for questions and answers so that we can help address any questions you have. We anticipate that hopefully you have a few as you'll be doing this soon. So with that said, so the problem. So our project was about baseball and machine learning. So a quick baseball rules recap for anyone who isn't familiar. So baseball, you got the batter, he's got a round bat. You got the pitcher, he's got a round ball. And you got to hit that round ball with a round bat that's traveling close to 100 miles an hour. So the batter has about 0.4 seconds to decide where that ball is going to be, whether or not he should swing. It's really fast, and then he tries to hit it as hard as he can inside the park. And so the batter is going to want to do a lot of prep to try and figure out what the pitcher is going to do. So a pitcher is going to have a couple of different pitches. Based on how they hold the ball and how they throw it, it spins differently in the air. So a fastball is going to be usually a little bit straighter, but it goes really fast, as the name implies. A curveball is slower, but it loops down and spins throughout the air. So a batter has a very short amount of time to decide which pitch the pitcher has thrown, and then whether or not they want to swing at it. So the best batters are people who watch lots of game film, and they try and really understand the tendencies of each of the pitchers. What will they do in different situations? And we wanted to see if we could help out the batter to come up with a solution that would give them a little bit of an edge. And context for this as well is that Major League Baseball has seen a lot of analytics throughout its history. It's nothing new. I'm sure most of you have heard of Moneyball. However, what they haven't seen a lot of is in-game analytics. Most of the analytics that have happened have been static. So you'll have an analysis of which players are worthwhile or who they should invest in. But what you haven't seen is players in the moment saying, we should do this strategically based on what happened last inning. Or we want to react differently because of something we're seeing in the game. So that's about to change. Major League Baseball recently discussed having iPads in the dugout be legal for the first time for the next couple seasons. And the world of baseball analytics and sports analytics in general are moving from this static model into this dynamic model. And we were excited about that and wanted to get on board. Also, how much can we help a batter? It's a huge deal if we can give them even a little bit of a hint towards what pitch might be coming next. So Hank Aaron, one of the most successful baseball players of all time, Hall of Famer, said that guessing what the pitcher is going to throw is 80% of being a successful hitter, and the other 20% is just execution. So here you have a world-famous baseball player saying, if we can solve this problem, we have gone a long way towards shifting the balance in the favor of the batters. And that was the motivation for our project. So given that we have this ball coming at us at 100 miles an hour, what do we do? Also, just to frame it a little bit more, you have the margin of error is very small, but as we were saying before, the small increase can lead to a big benefit for the player. So let's say you have 10 at-bats, 10 opportunities to hit the ball. If you get 2 out of 10 right, and consistently over the long period of time you get 2 out of 10 as hits, you're probably not going to cut it as a Major League Baseball player. It's a batting average of 200. It's not very good. If you get 3 out of 10, that's fantastic. that's like an all-star level. Just that 1 in 10, if you hit it and it happens to fall into the infield and you're safe, it's a huge difference. The best baseball players ever have hit about 4 in 10. And that is just astronomically good. Rarely does anyone even come close to that anymore. So if we can just help them 1 in 10 times, we have dramatically improved the outcomes for these baseball players. And there's a monetary value on this too. An additional win is valued at something like $5 or $6 million if you look at contracts and baseball kind of reverse engineer how much teams are willing to pay for wins. So there's a lot on the line with this project, and we're really excited to see if we can make a difference for these teams and these players. So next up, Josh will discuss the solution.
So what makes professional baseball more suited than perhaps any other sport for a data science solution is that the sheer amount of data available is just tremendous. So each team plays 162 games a season, and in each of those games, there's 27 at-bats for each team. And each of those at-bats then has usually 2, 3, 4, or even more pitches. So even just a couple of seasons worth of data will have thousands worth of pitches of data that we can draw upon. Oops. So that in mind, on a macro level, it's only natural we turn to computers to analyze this treasure trove of data that we have available to us. The solution that we settled on was essentially taking all this data that's present, that's available online through other sources, and just essentially feeding it into a computer and letting the computer decide, okay, we have all this data. Now, what are the best predictors of what a pitcher will throw? What are best predictors that will essentially read a pitcher's mind? On a micro scale, there's a couple of areas where a predictive model could have gone as a sort of a proof of concept or solution. But what we settled on was making a Twitter bot, because as Jason mentioned, we wanted to have a real-time solution to show that this could be accomplished in-game. So not only do we want to demonstrate that we could predict pitches, but we want to demonstrate that we could do it while the game was going live. Next, I'll be going a little bit over how this model actually works. So one handy tool that Major League Baseball provides online is its online scoreboard system. It's called MLB Game Day. What it does essentially tracks every single pitch of every single game. The in-game situation, the batter statistics, the pitcher statistics, the game state, who's on base, even things like weather, the ballpark. Pretty much every single piece of data you want about a baseball game is inside its online scoreboard. And the neat thing about this is that they make the XML files that power the scoreboard available online. So you can go into their back end and just start pulling down XML files of every single game of every single season dating back to 2008. So it's a quite comprehensive source of data we have to work with. So we found an open source library called PyGameDay that was able to go through this data and convert these XML tags into SQL format, so it's usable as a database. So we went ahead and modified that open source library to go ahead and iteratively pull down every single game since 2008 and feed it into an SQL database, which we then, in order to make it more accessible from an online collaboration environment, we decided to go with Amazon Web Services as our cloud provider. So we went ahead and put that into S3 and Amazon Redshift, which we use as our single source of truth database. So next we begin sifting through this amount of data we collected to see what exactly would be useful inside all this data. We wanted to determine what sort of predictive features would be useful for our model to analyze. So this included basic, readily available data, I mentioned earlier, such as balls, strikes, number of men on base, things that you would traditionally consider a pitcher might be thinking about when they decide what pitch to throw. And we also decided to build some of our own features that, on the surface, might not seem like they have too much relevance, but might be lurking somewhere in a pitcher's subconscious. Things like how well the batter has done previously against a pitcher. So if the batter has traditionally hit the pitcher very well, the pitcher might be more conservative and throw pitches that either nibble the edge of the plate or throw more off-speed pitches that have a less chance of being hit. Or say if the batter historically has done well against a pitcher might attack them aggressively with fastballs that they know the batter can't catch up to. Next, Zach will talk about how we convert this massive data into a usable machine learning model.
Yep. Thanks, Josh. So how does all of this work? Like we've kind of given you this broad picture of the context. Like what did we actually do to make this work, to make all of these features? And so here's kind of like our pipeline of what we decided to do. Well, first, Josh told you we pulled all of this data into a central repository so that we could collaboratively pull it down and work on it in a concurrent fashion. So we have it in Amazon Redshift, and then we would pull it down and we would work on it. And the real secret sauce of what we did was in this, we built this pitcher object using some object-oriented programming. And the secret sauce with this is we have this pitcher object that's basically traveling around, building features inside of it, documenting when a model was built, what models were built, the accuracy of it, what the data split was. It's basically kind of this model management built into it so that it's keeping track of everything that's happened. And remember, we're doing this on a huge scale. We're actually building a different model for every single pitcher in Major League Baseball. So we're doing this for every single pitcher and giving them their own class and their own object. Now, when we do that, we pull the data down to raw form, and then we create all of these features inside this pitcher object that Josh just talked about. Everything from the game state to how the pitcher has done previously against that batter. And the other thing, because of, we had this tension, right? Because we're trying to build a pipeline that can build models for hundreds of different people, while at the same time being very accurate across all of them. Now, if we were just concerned with one pitcher, we could build specific features for that individual pitcher that might be unique to him. But if we're trying to do this over a lot of pitchers, we have to find out some kind of way to make decisions for each unique pitcher, but do it in an automated fashion. So one of the things we found that was really helpful was when we started looking at the data for pitchers, we noticed that over a period of time, pitchers' behavior actually changes. So a pitcher, Roger Clemens, when he came into the game in his early 20s, pitches way differently than he does at age 40. Now, if we're training our models on all of that history, we probably actually don't want to train on his habits when he was a naive 25-year-old, but we want to look at more of his recent data and weight that better, give that greater weight. So what we did is for each pitcher, we went through all these different date subsets, and we said, okay, what is the best range of data we should use to train this model to be most accurate? And after we did that, we also, again, I'll talk about this a little more in the next slide, but different models work better for different pitchers. Like, they have very different behaviors, and so we have to try to account for that. And one of the ways we did that was we had this methodology for building different models and trying them out in an automatic fashion for all of the pitchers. Secondly, we have to manage all of these models and be able to call them whenever they're needed. So the last thing we did is we saved these models out and we documented when the models were built and what data was used. And then finally, when it was game time, we loaded up our Twitter bot and we said, load up the models that we built and now go to the MLB Game Day servers that are producing live data and pull that down, run them through the models, and give us predictions and tweet them out so that people can see how well we're doing, so we can have some transparency as to whether we're accurate or not. Okay, so something we thought you guys might be a little bit more interested in too is in doing this whole thing, we noticed that different models were working better for different pitchers. So what we did is that we looked at the models that were working the best across all pitchers for the features that we were building, and we built a model. Used logistic regression, SVMs, random forest, and gradient boosting machines, and then we combined them and produced all these different combinations and ensembles, and then we tested them to see what unique combination works best for every single pitcher. And so then that was the unique pitcher-specific ensemble that we used, and we developed that pipeline to do that automatically for the pitchers in the MLB. So the big question is, how did we actually do? All right, so I'm going to talk about this on a couple different levels. But first, I want to direct your attention to this graph on the left. So this is, we randomly sampled 50 pitchers to train models on using this methodology. And we saw, like, if we have this naive baseline, if we just guess the most common pitch every single time, how much better are we doing than that? And so this left histogram is an example of what were the accuracy increases over that baseline. And some of them seem modest. Some of them are actually really good, especially when you consider the fact that if you can give a hitter just a little bit of insight, like there's actually big, big ROI for even just a couple more hits in a game. And then this distribution on the right is if we were to just guess what would our accuracy be over these 50 pitchers. The blue is, or purple, I can't really tell, is if you were to just guess the same pitch every time, and we see that distribution for our model, which is green, like what the accuracies were when you used our models. Now, what's most interesting about this when we dug into it is that our mean accuracy improvement was 5.3%, which is okay. But the standard deviation was almost equivalent to the mean. And so what this showed us as we dug into it is that some pitchers were actually much more predictable than others, right? Or at least given the feature set that we were using. We could build out more features, and maybe we would have better results. But we noticed that some pitchers are actually much more predictable than others given the game state. So here's an example of some of the pitchers out of this random sample that we drew, and the accuracy increases and improvements that we get across them. And so we get some nice accuracy improvements. But I'm going to come back to the slide in a second because we don't think that this tells still the whole story of what is most interesting to an MLB team if they're really trying to use our predictions and signal to batters within that 20-second window between pitches. And that brings us to our lessons learned. So we wanted to both throw out there what we think we did wrong and what we did right from the beginning and the biggest impact we think it had in terms of helping us be successful. So the first lesson is, I think, is to let the domain and the problem define your success criteria, or at least even your model success criteria. So right here, we were basically using lift and accuracy improvement over a baseline. But when we started kind of like thinking about and talking to people that played baseball, this is saying like over all pitches, how much more accurate are we? And then this assumes like we would be signaling maybe to a batter every single pitch what like they should expect. But in a batter's mentality, they're very superstitious creatures. If you don't know, they do weird stuff. There's an interesting paper or theory that as success rate is lower, people become more superstitious, and baseball has low success rate. But anyways, there's this idea that what if in every 3 pitches, we could tell someone with 90% accuracy what the pitch was going to be. That would actually be much more helpful to a batter than just saying, well, overall, you're going to be this percent like more accurate. If we could actually calibrate the probabilities and say, we are sure that we've got the right probability on this pitch, and now we signal to you only on select pitches or in certain situations. So we didn't show that slide here, but we went back and calibrated probabilities to make sure that our probabilities on each prediction were matching reality. And then we think we would actually subset that down to a set of like what we would signal to batters. So it would change our success criteria based on what would be useful to the hitter. And then I think the second thing that helped us out a lot is actually really a tribute to Jason, who proposed the idea, is that when you vote for projects and you assign your points to what you want to sign up for and work on, the reason I chose to work on this one with Jason was and Josh and Alan was because it was very well scoped. It had a very well defined goal. It was doable within 3 months. Jason laid out where the data was and made it clear what was needed to transform it. And the other projects I heard, and they were all ended up being great, but the initial proposal was a kind of boiled the ocean kind of problem. It was like, we're going to change the world in 3 months with data. And those were cool, and I think a lot of people were drawn to those projects, but they were awesome ideas, but I think they were out of scope. And so my encouragement would be to, when you scope out your project, answer a few really practical and specific questions of where is the data? Do we have are you reasonably sure that this can answer the question we're interested in? And how do we tell if we're successful or not? And those seem very basic, but those were the main reasons that being able to answer those well were the main reasons I think we succeed in this project. And these guys have some other thoughts as well.
So my lesson learned is more of a lesson learned throughout the whole MIDS program. Someone with barely any technical background going to program. So I'm a tax accountant by trade. I thought building out these complicated data science models and visualizations throughout this program was really, really quite intimidating. Beyond the scientific knowledge necessary, just figuring out how to properly implement all these diverse models in a variety of languages and formats, it just seemed like an impossible task. Someone that just did Hello World a couple weeks before the program. So with that in mind, one of the most important lessons I learned through the program was how to Google. So nearly all the programming tasks I encountered were solvable through knowing how to Google the right phrase and hack together solutions based on appropriate documentation, questions people asked on Stack Overflow and various open source repositories. As long as I have an idea of what I want to build in my head, it's just really a matter of time and a lot of search queries until I could find the right snippet of codes to piece together and build what I wanted to build. I guess sort of find actually the lesson from a data science program being that having access to large amounts of data and clever ways to search it being really, really useful.
Yeah. Also, I forgot to mention this in my introduction, but we were a 4-person team. You will see 3 of us up here. Alan was instrumental. He couldn't be here today, unfortunately, but he was very much a part of this process. So I have 2 lessons learned, one kind of quantitative machine learning specific, and one more qualitative about the Capstone in general. So first the quantitative one, because I know my audience here. One of the main challenges we ran into in this project was the dependent variable. So which pitch type it was something that was sort of inconsistent. Major League Baseball figured this out, and our source of truth was they had these cameras that watched the pitch that every Major League Baseball team set up at their stadium, and then automatically classified with a neural net which type of pitch it was. But they changed their neural net over the years, so the dependent variable was a moving target. And that made it very tricky, and we did quite a few things to try and adjust for that, and the date subsetting ended up being part of that. But when you're going into doing a project, especially a capstone or something where you have a dependent variable, we talked a lot in field experiments and other classes about being careful about your X variables, and those matter. There's no question you need those to be clean. But you can sort of adjust for that because your models will filter for the X variables to some extent on their own and ignore them if they're not good. But you need your dependent variable to be great. You need to have a really clear picture of what that target is if you're going to be able to hit it. So that was a challenge that we faced, and I think did a pretty good job of working around. On a less technical level, so I had been thinking about doing this project for a year prior to the capstone, and I was thrilled that I got to do it as part of my capstone. I think going into the first class to sell the project, one of the advantages that I had was that there's a very specific vision of using this tool in a cool way. So I had this image that I tried to paint of sitting in a baseball stadium next to a GM with an algorithm and having the GM predict what his pitcher was about to do and having the algorithm beat him. And I kind of used this as an imaginatory way of getting people excited about the project and the whole process. And I'm as far removed as Elon Musk as you can be, but Elon Musk talked about this with SpaceX, where you have he talked not about the technical specifications for a rocket, but the image of a red planet Mars with a green plant growing on it, and how that image, like literally a photo in his mind, was a huge motivating factor, and it's something that he could pitch to people to align the whole organization towards what they're trying to do. And I think having that image, on the one hand, it feels kind of hokey because it's like, okay, that image may or may not happen, and it's this very emotional appeal, and we're all data people. But it really crystallizes that there's value in your project. If you can have a specific image, a specific outcome that people will know is exciting and something that you can get into, it goes from being one of those boil the ocean situations to one where you actually have something tangible to work towards. So I would try and find an image of what's a realistic best case scenario if this works, and then use that to pitch your classmates, because there were a bunch of people in our class and a very small number of projects that happened. So if you want your project to happen, you got to pitch. So with that, we're going to move to question and answer, and we're happy to answer any questions you have about our project, about MIDS, about the Capstone course, or anything else you'd like. So thank you.
We've got about 6 or 7 minutes for questions here, and then we'll take a break at 3:40. So please, feel free, guys, come forward on the stage there.
Yeah.
Right at the back, yes.
Hi. So I'll preface by saying I am not into sports in general, so this is coming from that angle. But earlier today, the very first talk, there was the example of sports racing and why is it a sport? And it's a sport because all the cars are the same, and it's about skill. And so I'm wondering, with things like this, how is baseball eventually going to still be a sport if it's all about what iPad apps you have and how good your data science team is? So I'm not saying you're ruining the sport you're interested in, but I'm wondering what your take on that might be.
Yeah, I think that's a great question. And my answer to that, and we actually talked a lot about this sort of spirit of that question in the ethics class with Anna. What I would say is, we did not invent the idea of analytics in baseball, and I don't even think computers invented that. I think that the idea of using information as best you can has been around as long as the sports existed. And there's no question that these tools change the game. And now part of being a successful baseball team is having good analysts as part of your team as well. But fundamentally, the game is the same. So a question we got pretty often when we were developing this is, okay, you have this algorithm. Let's say it's super accurate at predicting what a pitcher will do. Well, couldn't the other coach tell the pitcher what the algorithm said? And you can use that to go back and forth. And it starts this whole cat and mouse game between the two where they're both trying to guess what the other happens, or what the other one's going to do. If you take a step back, that's already what's happening in baseball. You already have batters watching game film to try and figure this out, and pitchers watching what the batters do to try and counteract each other. So I see this as the next level of sports, as a way of appreciating it in a new way, as opposed to detracting from the spirit of the game itself. It's still won and lost on the field.
Yeah. Wait for the microphone a moment, thanks.
Yes, I'm wondering if you find any correlation between because I would think the best pitchers are probably less predictable, right? So did you find any correlation to pitchers where the model didn't work as well and their ERA,
Shall I take it or you want to? Yeah. Okay. So there's some other people who have done work with this sort of problem, only a few. I scoured the internet because I was sure that someone had already solved this problem, and that was not the case. There was a paper that happened right before we started our capstone looking at a correlation between ERA and predictability, and there was a very weak correlation in the direction you're suggesting. However, I don't think that's universally true. So the example that the batter, or a previous author working on this problem gave is Mariano Rivera, who for any baseball fans, he's one of the best pitchers in history, and he had one pitch, and that pitch was a cut fastball. And pretty much every time you went to the plate, you knew you were going to get cut fastballs, and you probably still couldn't do anything about it. So some pitchers, they have different strategies. Some try and be really unpredictable, and their stuff isn't as good, but their strategy is better. Other pitchers rely more on raw physicality. So it's not like a perfect correlation. There are some really good pitchers who are rather predictable. There are some really poor pitchers who are not. It depends.
Right in the front here.
Thanks for the presentation. That was really interesting. Going through your capstone project, what was your biggest struggle, your biggest difficulty, your biggest gap in knowledge that you had to overcome to make this thing happen?
Yeah, I don't know if there was as much a gap in knowledge that was felt, because I think, so when we were first starting out, we were building some of these models and we weren't getting great results, and we just kept asking why, and so we felt like there was maybe some gap in knowledge, like did we not know should we be using a different machine learning technique? Should we have just thought about something else in a different way? And so the great thing about the capstone course is that we have these breakout sessions, and we would have some of our advisors come in and we'd just pitch to them and say, this is our problem. We're trying to think about how to do this correctly. A lot of that kind of led us to the date subsetting of not just using all of the dates, but realizing hey, our dependent variable isn't completely clean. We need to do something to adjust for that. But that's where our advisors came in, and they really helped us see that there wasn't a gap in our knowledge, but they helped us brainstorm about okay, let's think through this problem. What technique can you use, or what could be wrong? And so I didn't feel like there was ever necessarily a gap, at least technically, in our knowledge. I think we were being pushed along throughout the project by some of our advisors to consider the problem differently, and that was really helpful. They never solved the problem for us. They just asked us questions that we should be considering.
Yeah, let's take a final question here. Thank you.
I was just curious if you tried looking closer at grouping particular pitchers. and seeing if there was a similarity between certain types of pitchers. Like, I'm not a baseball fan either, so I can't really speak in too much detail what you could have done, but maybe if some pitchers seem more random than others, then your accuracy might have been better, or maybe if they were more predictable, then machine learning might not have been the best type of predictive model to use. Maybe something like a Bayesian model or just a simple average or something, for instance, might have been more accurate. Did you see any kind of potential grouping like that? I'd be really curious to know.
Yeah, so I'll let these guys speak to it, but we have a laundry list of things that we want to still look into, and once we get over this like sigh of like we're done, we want to actually come back and keep working on it. So that's one of the things, and it's more generally is are there global features of pitchers that we can include in our models that will make them more accurate, so that we can use like not just single in and look at like a specific pitcher and all of his past history, but maybe look at either pitchers as a whole or different subsets of pitchers and their tendencies and behaviors. Because if we can do that, a lot of times, like, we have limited data sometimes for these pitcher-batter interactions, right? Because maybe a pitcher has only seen a batter a few times, and we account for that already, like in basically having this weighted global versus like specific average of what he's done. But it would be more helpful to be able to bring in other pitchers that were like him, to bring in some of those variables. So that's a great suggestion and something we're thinking about.
Yeah, as Zach said, so it's one of the things we talked about very early in the project, which we didn't end up doing, but is still interesting, I think, to all of us. And I think this was Alan's idea originally, was having like a mixed model that was part pitcher, like the specific pitcher, and then part a whole pitch, like all the pitchers in one. Like, you train two sets of features basically. You have like all the pitcher features and then your pitcher specifically, and that you can kind of trade off between the two in like a Bayesian way. We tried to kind of proxy for that a little bit with the prior variables. You saw them very quickly on the screen, but you could balance between the two. So if a pitcher hadn't really seen that batter before, you built in global averages that you then set a constant value to. So for us, it was 4. So you got like 4 pitches worth of the global, and then you could, like average that in with the batter specific, like that batter against that pitcher's history. And then over time, as there's more history, the batter-specific part swaps. But that was just one part of our model, and it would be fascinating to have a mixed model in that way. So definitely something worth investigating in the future.
Great. Much more work to do. Thank you guys for a great project and a great way of